Now we move on with a new assumption in the model. Now remember this whole chapter, this whole lecture, the theme, the topic is transitions. And in the first session of this board, first session of this lecture, I was saying a transition could be from one state, one stationary state, to another, okay, over time. So you have a perturbing potential H dashed, which causes that transition, that switch from one state to another. So in terms of the math, now that we've got some interesting equations for A1, the first order correction to the A coefficient in your expansion of psi of R and T, we can use that now. Let's do a concrete case, an application of that theoretical model, and let's assume that your perturbing potential H dashed is now just a harmonic oscillation. Now, if in physics or math, if you hear the word harmonic, you're just thinking oscillation, right? Something like this. So a sine or a cosine, that kind of thing, and comes from the word, obviously, harmony, which has something probably to do with music. Okay, so a pure single frequency note is a harmonic. So from the term, for example, simple harmonic oscillator. Well, it's almost a repeat of terms. An oscillator and a harmonic are pretty well the same thing. So a simple harmonic. So what we're going to do here is the perturbing, the H dashed, is going to be a harmonic of a fixed amplitude. We'll call that H bar. So the bar, you know, I'm getting ahead a little, but it's just an intro to the session. This term here, that's assumed to be a constant as far as time is concerned. It may vary on the position. It might be a function of R, but the bar here, just think of as not depending on time, right? Because there's no t in this expression. But there is an explicit, in the formula, dependence on time, t here, with this term here. So here's your harmonic, right, of a given angular frequency omega. Okay, so you'll apply this perturbing Hamiltonian H dashed. It'll be of this form. This part not depending on time, and this part explicitly depending on time, and oscillating, going up and down in a harmonic way at angular frequency omega. Okay? So we will apply this H dashed. We'll plug it into the perturbation matrix in the integral that is in the expression for A1 that we found earlier. Okay, so, but I'm getting a bit ahead of myself. So let's start our initial state at time 0, if you like, when the perturbation, when this sort of thing starts at time t is 0. So we switch on the perturbation at time t equals 0 and let it run for time t. We will then get a value for A1. Now in the previous session I labelled that equation for A1, AM1, first order correction in the perturbation theory. I labelled that star circle, and you can't see it, I'll just read it out again, or you can go back to the previous session and have a look. It's 1 over IH bar integral, sigma over n of A to naught, so AN of naught, integral naught to t, H dashed Mn, so there's your perturbation matrix elements, Mn, the nth element of that matrix, e to the I omega Mn t dashed dt dashed. Right? That's that star circle equation. We're going to assume at time t equals 0 at the beginning, the initial state is just one eigenstate, one energy eigenstate from the Schrödinger time independent equation. So all the UNs will be 0 except 1. Right? And so all the corresponding coefficients, A, time independent coefficients, will be 0 except one of them, which will be 1. Now let's say we choose the kth eigenfunction to be that initial state. So the system, your quantum system, starts off at time is 0 when the perturbing Hamiltonian is applied. There'll be some, here it'll be some, the potential energy, say, is depending on time. That's an example. We'll talk about this next square. Right? So let's assume that we start off in the eigenstate, just one eigenstate of UK, not UN, UK. So all the other n's, ANs, are 0 for when n is not equal to k. Right? So the equation that I just read out before, star circle. That will simplify because all these ANs are 0. The sigma term will drop out. The AK coefficient, AK naught, to the 0th order correction, that will be 1. So the sigma drops out. The A naught terms drop out. You just one of them remains, but it's value 1. Right. So that expression for this in the previous session simplifies a lot. The sigma terms dropped out, the A's have dropped out, you just left with a single 1 here, not even written, and you just left with this expression. Okay? So, now if, you can just see from this by inspection, say you're perturbing Hamiltonian H dash is very small. Well, effectively, 0. So it means that these corrections to first order in time will also be very small. If h is very small, the whole integral is very small. Okay, so these corrections will be very small. So that intuitively makes sense, which is what's being said here effectively. All right, now these A's, these coefficients in the expansion of a wave function in terms of complete orthonormal eigenstates, we've interpreted them in the past as probability amplitudes. Remember amplitude, you have to square it, you get a probability, probability density. So we'll assume the same interpretation here. So if we square this, that will give us the probability, I'll just shorten to prob, the probability that at time t later, remember the perturbing Hamiltonian is assumed to switch on, become active, at t equals 0. So time t later, this will be your probability amplitude of what? Well, if you square it, that's the probability density that the state has switched or transitioned. Right? Transition. Remember, that's the whole theme. It's the very label of this whole chapter, chapter 11, last chapter in the book, and end of this undergrad course. So this gets interpreted as being the probability that at time t, that during that time, between time 0 and time t, in that time interval t, that the state of your quantum system has transitioned or changed from UK to UM. Okay, it's made a transition. So that's interpreted as the probability that transition has occurred from state K to state M. Right? That's how this is interpreted. Now, from the HUP, the Heisenberg uncertainty principle, you don't know exactly when that transition occurred. like if you're talking in terms of the model, the Bohr, B-O-H-R, Niels Bohr, atomic model, 1913. When does the quantum jump of the electron occur? From say an excited higher energy state to a lower one?